The directions say to find the exact area of the surface obtained by rotating the curve about the x-axis. The formula is S equals the integral of 2 pi y ds, where if y is a function of x, then ds is the square root of 1 plus dy dx squared dx. And then if x is a function of y, then ds is the square root of 1 plus dx dy squared dy. Let's take a look at some examples. Suppose we have y equals x cubed, where x is greater than or equal to 0 and less than or equal to 2. dy dx is equal to 3x squared. If I take dy dx and square it, I get 3x squared raised to the second, which is equal to 9x to the fourth. So S, plugging it into the formula, is the integral from 0 to 2 of 2 pi y, where y is x cubed, times the square root of 1 plus 9x to the fourth dx. And remember, dy dx raised to the second is 9x to the fourth. So we're going to solve this integral by u substitution. I'm going to let u equal 1 plus 9x to the fourth. du is 36x cubed dx, and then x cubed dx is 1 over 36 du. Plugging in, when x is 0, u is 1. When x is 2, u is 145. And so S is pi over 18, or 1/18 pi, times the integral from 1 to 145 of the square root of u du, which is pi over 18 times 2/3 u to the 3/2, evaluated from 1 to 145. So applying the fundamental theorem, this is equal to pi over 27 times 145 to the 3/2 minus 1. And this can be written as pi over 27 times the quantity 145 times the square root of 145 minus 1. Let's take a look at example 2. Y squared is equal to x plus 1, where x is greater than or equal to 0 and less than or equal to 3. Now we can solve for y and write this as y equals the square root of x plus 1. Because notice my limits are in terms of x, and so I want to express y as a function of x. So y equals the square root of x plus 1, free and clear. dy dx is equal to 1 over 2 times the square root of x plus 1. If I square it, I get dy dx squared is 1 over 4 times x plus 1. Okay, plugging into the formula, we get S is the integral from 0 to 3 of 2 pi times y, where y, if we write that in, is the square root of x plus 1. So S is the integral from 0 to 3 of 2 pi y. This is y. And then we're going to multiply this by the square root of 1 plus 1 over 4 times x plus 1. And remember, 1 over 4 times x plus 1 is dy dx squared. So I'm going to get a common denominator within the radical. And so I'm going to write this as follows. This is the integral from 0 to 3 of 2 pi times the square root of x plus 1 times the square root of 4 times x plus 1 divided by 4 times x plus 1. So remember that 1 can be written as 4 times x plus 1 divided by 4 times x plus 1. As long as x is not negative 1, of course. Now, going forward, this is 2 pi times the integral from 0 to 3 of the square root of x plus 1 times the square root of 4x plus 5 divided by 4 times the quantity x plus 1 dx. The square root of 4 is 2, and so this is 2 pi times the integral from 0 to 3 of the square root of x plus 1 times the square root of 4x plus 5 over 2 times the square root of x plus 1. And notice how the 2's cancel and the square root of x plus 1's cancel. And then from here, we get pi times the integral from 0 to 3 of the square root of 4x plus 5 dx. I'm going to let u equal 4x plus 5. Du is 4 dx. Dx is 1/4 du. Now, remember, when x is 0, u is 5. When x is 3, u is equal to 17. So this is pi over 4 times the integral from 5 to 17 of the square root of u du. So this is pi over 4 times 2/3 u to the 3/2 evaluated from 5 to 17. So this is pi over 6 times the quantity 17 to the 3/2 minus 5 to the 3/2. So this is pi over 6 times the quantity 17 root 17 minus 5 root 5. And that's the answer to example 2. In example 3, we have y equals cosine of 1/2 x, where x is between 0 and pi. Notice how y is a function of x. dy dx is equal to negative 1/2 sine of 1/2 x. dy dx squared is 1/4 sine squared of 1/2 x. So s is 2 pi times the integral from 0 to pi of y, which is cosine of 1/2 x, ds, which is the square root of 1 plus 1/4 sine squared of 1/2 x dx. And I'm going to do this by a substitution. I'm going to let u equal 1/2 sine of 1/2 x. du is 1/4 cosine of 1/2 x dx. So cosine of 1/2 x dx is 4 du. When x is 0, u is 0. When x is pi, u is 1/2. So plugging all this in, we got 8 pi times the integral from 0 to 1/2 of the square root of 1 plus u squared du. So notice over here, I drew a triangle to help me with my substitution. And this is a classic trigonometric substitution problem. I'm going to let u equal tangent theta, right? Remember, opposite over adjacent is tangent theta. So that's what I'm getting over here. So u is tangent theta, du is secant squared theta d theta. Square root of 1 plus u squared is secant theta. So 8 pi times the integral from 0 to 1/2 of square root of 1 plus u squared du is 8 pi times the integral from u equals 0 to u equals 1/2 of secant cubed theta d theta. And I've derived the integral of secant cubed theta d theta in different videos. I know I have at least one video where I have derived this integral. So I'm going to take the liberty and use it. So this is 8 pi times 1/2 the quantity secant theta tangent theta plus natural log of the absolute value of secant theta plus tangent theta evaluated from u equals 0 to u equals 1/2. if I go back to the triangle, you're going to find that we get 4 pi times the quantity u square root of 1 plus u squared plus natural log of the absolute value of u plus the square root of 1 plus u squared, evaluated from 0 to a half. Plugging in my information, I get 4 pi times the quantity 1/2 times the square root of 5/4 plus natural log of 1/2 plus the square root of 5/4. And so I did a lot of simplification here. Couple things to keep in mind is that the square root of 5/4 is the square root of 5 divided by the square root of 4, which is square root of 5 over 2. And so this is 4 pi times the quantity 1/2 times square root of 5 over 2 plus natural log of 1 plus root 5 minus natural log of 2. Okay. Now, this can be written as pi times the square root of 5 plus 4 pi natural log of 1 plus the square root of 5 minus 4 pi natural log of 2. And that's the answer to example 3. In example 4, notice that we have x as a function of y. So here, x equals 1/3 times y squared plus 2 to the 3/2, where y is greater than or equal to 1 and less than or equal to 2. So we're going to integrate with respect to y. dx dy is 1/3 times 3/2 times the quantity y squared plus 2 to the 1/2 times 2y. So that's just chain rule. But one thing I want you to notice is that the 3's cancel, and so do the 2's. And what's left is y times y squared plus 2 to the 1/2. Square both sides. And when I do, I get dx dy raised to the second is y squared times y squared plus 2. And if I distribute the y squared inside, I get y to the 4th plus 2y squared. Now what I want to do is add 1 to both sides. And so 1 plus dx dy squared is y to the 4th plus 2y squared plus 1, which can be written as y squared plus 1 raised to the second. Now I get to plug stuff in. So s is the integral from 1 to 2 of 2 pi in y, and we use y because we're integrating with respect to y. And then we're going to multiply by the square root of y squared plus 1 to the second dy. But this is the integral from 1 to 2 of 2 pi y times the quantity y squared plus 1 dy. Now what I want you to do is distribute that y inside. And we get 2 pi times the integral from 1 to 2 of y to the 3rd plus y dy, which is 2 pi times the quantity 1/4 y to the 4th plus 1/2 y squared, evaluated from 1 up to 2. And so I plugged in 2 for y, and then 1 for y, and then subtracted the results. And so what I get is 2 pi times the quantity 4 plus 2 minus 3/4. That's right here. And if I go ahead and simplify, you're going to see that we get 21 pi over 2. And that'll do it for this video. And we did 4 examples of finding surface area. Thank you.